Hey guys, this is Logic Crazy and I'm Jonathan, and welcome to yet another advanced Java chess engine tutorial. In this tutorial, we're going to be learning about transposition tables and Zobrist key generators. Now, these sound like real complicated words, but really the concepts are very simple if you can grasp a hold of a few key concepts that I'm going to be teaching you in this tutorial. So, to get started, what is a transposition table and why do we need it? Well, basically, when an engine is searching, it is very useful for, as far as speed is concerned, to be able to remember positions that it had previously looked at. So when it sees that position again, it can instantly remember what it had found out before. For instance, the best move that it found from that position, the evaluation, and things like that. So what we need to do is take all our positions and somehow store them in the computer's memory in a way that we can search and check if we'd already seen that position very, very quickly. So what we do is we create this thing called transposition table, which is really a one-dimensional array with a few fancy features. And this array is usually very, very big. There'll be several million indexes probably in a given array, but each entry in the array is very, very small as far as memory is concerned. So it won't actually take up that much physical space on your hard drive or RAM. So what we do is, in this array, we need to store a chess position, but you can't just insert a picture of a position into each item in the array. An array needs to store numbers, concrete data types like that. So what we do is we're going to store numbers. So we're going to take a chess position and turn it into a unique number that represents that position. And then we will store the information about that position represented by the number, so best move and so on. And then when we rediscover that position, our engine will again convert it into the same number, and we'll be able to find that number in our array. So for instance, we take this position here on the left. This is a unique position, and we'll run a certain algorithm called a Zobrist key generator, which will take this position and turn it into a unique number. For now, I've just set it to this number here on the right. So this position equals that number, 9365036. Then what we do is we put all those numbers into this array. So the bottom entry of the array is that position that we just showed, and other numbers represent their own unique position. Then what we're going to do is, when we search the board, we're going to come up to one of these positions that we'd already discovered that was here previously. In fact, this bottom position again. So we come up to that position a different way, and we go, have we already looked at this position? Because if we have, it would save us a lot of time just to remember what we'd learned about it. So what we do is we take that number and we again convert it into a unique number. And the algorithm will be the same, so we'll produce the exact same number, this unique number for that position. And then we're going to look through the array and say, does that number exist? And we'll look, and at the bottom, that number exists. So we're going to say, now all we have to do is remember what we'd learned about that position. So we'll zoom in to that array entry, and we'll look at all the data we've stored about it in the array. We'll store the best move from that position. Then we'll also store the current evaluation of how well each side is doing. Then we'll store alpha and beta, just in case we can narrow the search results if we continue to search. So these are some common things to store in a position. We'll get into that in another time. Now let's talk about Zobrist keys. These are those numbers that we've been discussing. How do you take a position and turn it into a unique number? I mean, when I look at a regular chessboard and look at a position, I don't think, oh, of course, that equals 5,374,000. I just think that's a position. I could take a picture of it, but I can't just turn that board position into a number in my head. But here's how we do it with computers. And one other thing I should quickly mention about Zobrist keys is you want to make sure that no two positions make the same number, have the same Zobrist key, because then you have confusion. You all of a sudden have two positions that both have the same entry, and then mistakes are made in the engine. So here's how we do it. We take this unique position, which I've grabbed just by a chess match between a couple engines, and we're going to try to turn this into a certain number. Now, we're not a computer, so we won't actually do the math here. But what we do is at the startup of the engine, for each of the 64 squares in our chessboard, this is, by the way, is just a zoomed in view of this position we're talking about here in the top left-hand corner. What we do is at the startup, for each square, we come up with 12 randomly generated numbers. Now these numbers are only going to be generated once, and then for the rest of the program they're going to stay the same. There's going to be a number for each of the 12 kinds of pieces. 6 of black pieces, 6 of white. So here I have represented white pieces using capitals and black pieces using lowercase numbers. So capital R would be a white rook, and so on. And I've only done 2 in this diagram, but each of the 64 squares would have their own randomly generated numbers. Then what we do is when we look at a position and want to turn it into a number, we go through the board scanning for all the squares that have a piece on it. We ignore the squares that are empty. So we first will find this black rook here at the top. And then we'll figure out what that unique random number was for a black rook on that square. Then we keep going and we'll find the unique number for a black pawn here in the middle of the diagram. And we'll go so on and so forth through all of the pieces on the 64 squares of the board till we come up with a list of unique numbers representing that particular piece on a particular square. Then what we do is we take all of those numbers and we XOR them together, which is a computer term meaning or but not and, basically. So it is just a fancy way of sort of merging different numbers together. Sort of like adding or subtracting, but this is a unique, different way which works with bits, ones and zeros. So what we do is we take all these numbers and we do an XOR thing to get them, and that's a really, really efficient operation for a computer to do. And it basically just combines these numbers in a special way. And we XOR all the numbers, as you can see from the arrows. Now these arrows are pointing from empty squares, but we would only be getting them from squares with pieces on them. And we get all these numbers and we XOR them all together, and then we get the total, and the total will be that unique number representing the entire position. Whatever that number was, it will represent this position. Now, it is possible to get the same number representing 2 different positions. However, the chances of that happening are 1 in many, many million. And the good way outweighs the bad. And in addition to that, there are different ways that programmers can eliminate these errors or make them at least very solvable and lessen the negative effects of having 2 positions referred to by the same, 2 different positions referred to as the same Zobrist key. So that's the basics of how transposition tables work and Zobrist keys. And we'll be getting into this in a lot more detail in the tutorials to come with the programming technical aspects of this. Thanks for watching. I hope you subscribe. and have a good day.